Today I'm going to up to now we had introduced in the other part 2 we introduced the external force flow, and today I'm going to start the internal flow. They have some similarity and also some differences. We will see how it is effective. Like what we had for the external flow, liquid or gas, for that kind of the flow, the fluid was going around something. But for internal flow, the fluid, which can be liquid or gas, can go through something like pipe or ducts. And it can cause some heat transfer between the fluid and the pipe and also the surrounding. What we are interested about is the convection heat transfer between the fluid, which is inside something, which is flowing inside something like a pipe or duct, and that pipe or duct or even channel. This kind of the pipes or this kind of the heat convection, heat transfer is mainly being used for the heating of the house, for example. I think you have seen some heater which they use the pipe, the fluid is going through, or water is going through that pipes, and it will increase the temperature of the surrounding. Now we are going to see how we can increase the heat transfer. How is the heat transfer, convection heat transfer between the fluid inside that pipe or duct and that pipe or finally their surrounding. So we are interested to use a fluid, for example, inside a pipe or duct to have a desired heat convection. For example, to warm a house, we use hot water inside some pipes, circular pipe, for example. Then by using that, we can increase the temperature inside the house. But for using this system, we should use a pump. For example, for this kind of liquid or water, we should use a pump to pump or to send the water to these pipes. So we need energy to send this water inside the duct or inside the pipe. Why we need energy? Because, as you know, there is a frictional effect between the internal surface of the pipe and between the fluid. That frictional force, which is dependent on some characteristics we will see, will cause the a stoppage or to reduction of the velocity of the fluid inside the pipe. So we should use a pump to continue the flow inside the pipe. We will also calculate the energy which is required, or the pump size, for example, to pump the fluid into the pipe or duct to have a desired flow in the pipe or duct. And as you may notice, usually the pipes are have a cross-sectional area like this. They are circular pipe. But you may don't know the reason for that. Actually, there is two reasons to have this kind of pipe. First of all, This design, which is circular cross section, can resist or its strength against the pressure is the maximum. In other words, compared to this configuration, this shape, for example, the circular pipe can stand with the higher pressure. You can use this pipe for the higher pressure. And as it is also mentioned here, for a fixed surface area, the circular tube gives the most heat transfer for the least pressure drop. We will see what it means. So it will give us also the maximum heat transfer. So usually the pipe which are being used for heat transfer in different devices by this internal flow are designed as a circular pipe because their heat transfer is the maximum. And also its pressure drop. What is the pressure drop? When the fluid it's going to the pipe, its pressure at the entrance will be different from the pressure at the, for example, if it is an open-ended pipe, will be different at the end of that pipe. Or even at any distance from the entrance, the pressure will be different and the pressure actually will be lower because of the frictional force between the fluid and internal surface of that pipe. We will also calculate that pressure drop, and we will include that pressure drop to use our pump. Our pump should be able to provide that pressure drop. It will increase the pressure constantly to compensate that pressure drop. Okay. Here in this figure, you can see an example of a flow inside the pipe. First, we should know how is the velocity of a fluid flow inside the pipe or a duct. Here you can see that a fluid which is flowing inside the pipe. Here you can see the vector of its velocity. You can see that the velocity of the fluid near the wall is almost zero, or we can consider it as zero. This is due to the no slip condition at the wall. So the speed of the fluid near the wall is almost zero. We call that no slip condition. And at the center of the pipe will be the maximum. The velocity of the fluid or flow in the center of the pipe will be maximum, Vmax. But for our consideration, we can say that all these fluid is flowing with a constant velocity, which we call that V average. So it is convenient for our calculation to use this V average, because it be very complicated if we consider the velocity of the fluid like this. So we can consider it as to have a average velocity as V average. This V average is usually defined by the Vmax, and it is usually half of the Vmax, which is for fully developed laminar pipe flow. We will see what is the fully developed laminar pipe flow. So we average for a fully developed laminar pipe flow is half of the Vmax. And also we will see we have similar thing to calculate the average temperature for the flow or fluid inside the pipe. Why we are going to use this average temperature and average velocity? Because it will reduce our calculation. We can find heat transfer more easily. We can find the required energy and the appropriate pump easily by some error. So first we should calculate the V average or average velocity and average temperature for different flow inside the or internal flow. From now on I will call that internal flow. It can be in the pipe or any other kind of the medium. Okay, first let us start with this average velocity. The average or mean velocity can be calculated by conservation of mass principle. This principle said that there isn't any loss or production of the mass for a differential part of the flow inside the pipe or any other media. So m dot is always constant. M dot to the for example a cross section of the pipe is equal to rho V average AC. Rho is the density of that fluid, V average is the average velocity, and AC is the area or the cross section for the flow. Rho V average, AC is m dot, and it is also equal to, we can calculate by this equation, integration of rho UR dAC. For this integration should be for the cross section area of the fluid flow. Rho is again density, UR is the relative velocity of the flow, relative velocity of the flow at the distance of the R from the center. Imagine this is a circular pipe, so in this direction we have R, or up lower R, actually lowercase r. So for different R, for example here can you again see the PowerPoint? Please open your mic, someone of you, just tell me if you can see.
Yes, sir.
Okay, thank you very much. Okay, let me use my pen to draw it. Okay, so this is R, as you can see here, and R means here, this is a pipe, okay, so the R, that R is this, and U is the velocity for each R. U, as you can see here, this is V average, this is U at this R. U at this R, different R. So this is relative velocity. So by this conservation of mass principle, we can write this equation. The mass for each cross-section area can be calculated by each one of these equations. By rearrangement of this equation, we can write V average equal to this value. Here we just rearrange this to find the V average. Then we can calculate this DAC, or the differential cross-sectional area, DAC. it is equal to 2 pi r dr. In other words, DAC means if, for example, let me draw something. I will try to. Oops. I will try to draw something. For example, here is cross-sectional area. It is something like this if we change our view for different R. Okay, so we just now we are going to calculate the sorry, this part is I don't know why it is showing. Ignore that. Okay, so we are going to calculate the area for that, the velocity, as we write. This is the differential, this is DAC. So this AC, this is dr, this part is dr, just its thickness is dr. So to calculate this its area, we can write this equation. This DAC is 2 pi r dr. By substitution of DAC in this equation, we can bring out this 2 pi, actually not r, 2 pi and rho we can bring out, because they are the constant value, we can bring out this value to the out of the integration. Then we can cross out the similar value. Then we can rewrite our equation like this. We have in this part only r square and 2, and we have this equation to calculate V average. This is the average velocity for incompressible flow in a circular pipe with radius of upper R or uppercase R. That was the average for average velocity. We have same procedure to calculate the average temperature. For average temperature, we should use the rule of the conservation of the energy. So we can write, it says that the energy in the whole system or control volume will be constant. We can write the energy to the system is m dot CPTM, thermal energy to the control volume is m dot CPTM. And for the with same procedure, for example, for with same procedure, imagine this is the again DAC, the energy or a dot to the system is m dot CPTM. Tm is average temperature, and also we can use this equation to calculate this rate of the energy to the system by this equation, CPTR del m dot, or like with similar procedure like what we had in for the average velocity, we can rewrite it like this: rho CPTRU URDAC. This is delta M, which we can write like this: rho UR DC is del m dot, which we had in previous. You can see here m dot rho v average or m dot rho ur DAC. Then we just put this m dot. Okay. Again, with same procedure, we can just rearrange this equation. We are interested to have this T average or T median. By rearrangement, we will have this equation. By substitution of the m dot and using this equation, we can rearrange it. This m dot, I show you in previous slide. What is it? M dot is here. We can use each one of these equations to put in our equation here. By the substitution, we will have this final equation for the average temperature. This is Tm, as you can see here. Actually, the temperature of the fluid inside the pipe is something like this. The temperature of the surface of the pipe is Ts. The temperature of the fluid here is the Tf, for example. And it will be something like this. Temperature of the fluid near the surface is equal to the temperature of the surface. Ts equal to temperature of T fluid. And in the middle of that, imagine here Ts is higher than T fluid. And you can see here, as much as we go further or far from the surface of the pipe, its temperature will be different. Here is lower because the temperature of the fluid is lower than the temperature of the surface. But we can imagine we have Tm. We can imagine we have a fluid with Tm, which is the T average. Temperature all of the fluid is T average. It is a imaginary value. Then we can calculate that imaginary value or T average like this by this equation, which is dependent on V average we had in previous slides and the radius of the pipe. Now let's see how the characteristic of the fluid is effective on this temperature and also the velocity of the fluid in the tube or pipe. As you know, flow in a tube can be laminar or turbulent according to its Reynolds number. In lower speed, it will be laminar. With increase in the velocity, it will change to turbulent. And this transition from laminar to turbulent occurs in some range, and it fluctuates from laminar to the turbulent. This fluctuation part is called the transient parts. When the fluid starts from laminar to change to the turbulent flow. But what is important is that most of the pipe which we are using for our application encounter the turbulent flow. Usually we have turbulent flow. And laminar flow is only for the application when we have a highly viscous fluid like oils flow in small diameter tubes or narrow passages, which is a specific cases we have this condition. And what is effective on this transition from laminar to turbulent flow? It depends on the Reynolds number. It depends on the degree of disturbance of the flow by surface roughness. So surface roughness is also effective on this this flow characteristic to be laminar or turbulent. The pipe vibration and also the fluctuation in the flow. These different parameters are effective on the flow, and they will cause a flow to change from laminar to turbulent. But usually we have a scale. If the Reynolds number is lower than 213, we call that the flow is laminar. If the Reynolds number is higher than 10,000, we call that turbulent flow. And between these two, we call that in the transition part or transition region. So this is the Reynolds number for internal flow. Please do not mix these criteria for the external flow and internal flow. This is for internal flow, and for the internal flow in the pipe, if the Reynolds number is lower than 2,300, it is laminar flow. Higher than 10,000, it is turbulent flow. Between 2,300 and 10,000 is the transient flow. This is a good scale for us to know if the flow in the pipe is laminar or turbulent. So how we can calculate Reynolds number for in a circular tube? We had Reynolds number. Please do not again mix this Reynolds number with the Reynolds number we have calculated when we had external flow. The appearance is same, but it is different. For the external flow, it was a ball or a sphere or a cylinder, and the flow was around that. But here the flow is inside something, inside the tube, inside the duct. So only the appearance is same. D is completely different here. V average and no. Again, V is velocity, now is kinematic viscosity, but D here is completely different, and we will see how we can use this Reynolds number, this equation, to calculate Reynolds number. So Reynolds number for a flow in a circular tube will be like this, equal to V average D no. V average we can calculate by the equation which I introduced you in previous slides. No is a characteristic of the fluid which you can find from the table. It depends on the temperature of the fluid, and D is the diameter of that circular tube. By rearrangement of these, and if you remember, this kinematic viscosity was equal to mu divided by rho. And if you put here, you can have this equation, rho V average D by mu. Then we can bring out this rho D by mu, substitute this V average from the previous slides. This is the rho average. If you go previous slide, you can find that. Then the final equation to calculate the Reynolds number is for m dot. M dot is mass flow rate of the fluid inside the tube by mu pi d. Mu is the dynamic viscosity of the fluid, pi is pi, and d is the diameter of the tube. So by this you can calculate the Reynolds number and say that if the flow is turbulent or laminar or transient. But usually we have other type of the object or pipe with different geometry. For example, we may have a square duct, we may have rectangular duct, we may have even the channel. Channel is something like this, which one side of that is open and it is not fully closed. Then how we can calculate the Reynolds number for the flow in this type of the media? Again, we can use this equation, but we should find a value for D. Here m dot mu pi, again it's characteristic for the flow, and it is constant. The only difference is D. We can use another characteristic, which is hydraulic diameter, or DH. DH is equal to 4 AC by P. P is perimeter in the direction of the flow, and AC is the area for the in the direction of the cross section area of the object in direction of the flow. So you can see here this hydraulic diameter for the square duct is DH equal to, if you just substitute the AC here is A2, so 480 divided by P. P is the perimeter, so it is only 4 times A. So DH, or hydraulic diameter for duct like this, with the size of any part as A, we will have A for its hydraulic diameter. For the rectangular duct, again we can calculate the area. AC is AB, for AB by this equation, for AB divided by its perimeter to A plus B. It can be simplified to this. For a channel, it's a little different. It is similar to rectangular duct, but difference is that you should only, because we have the friction and even the heat transfer between the duct and fluid, only for the parts or areas which that fluid is in contact with the duct. Here we don't have any duct, it is open actually, so we don't have any friction here, we don't have any heat transfer between the duct and the fluid. So in our consideration we should ignore that. So the area is again same for AB, but the perimeter or P is different. It is to A only this part, to A plus B. So hydraulic diameter here will be for AB divided by 2A plus B. Only for the duct, for the channel, we have something like this, a little different with the previous. This hydraulic diameter can be used to calculate the Reynolds number. Here we can put the H instead of D for all of these shapes. Also, it can be used to calculate for our Nusselt number calculation, and also to calculate friction factor. In next slide, we can see how we can calculate Nusselt number or friction factor for the internal flow in the pipe like this. And we should always use this DH in our consideration. DH for the circular tube is equal to D, so it doesn't change anything for our calculation. For other configuration also we should use this DH, and we should calculate by these equations. Okay, now we have some basic information and characteristic which we can use them to consider and evaluate the internal flow. Imagine this is a pipe and the flow is coming to or going through this pipe. Its radius, this pipe is R, and in this direction we have X, from the entrance to the end of that pipe, or in the X direction actually. When the fluid is coming to this pipe, its velocity will be something like this, as you can see here. It has a V average. The V is constant because it has not started to be in touch with the surface, and its velocity is uniform like this. V average is equal to V entrance. But when this fluid is traveling through this pipe, its velocity will change and finally will be something like this. Near the surface or wall of the pipe, its velocity will be 0, and at the center of that pipe, the velocity will be the maximum. But as I told you, we can find a V average for the velocity of the flow inside the pipe. But we categorize the different region according to the shape of the or vector of the velocity. Irrotational or core flow region is the frictional the part when the frictional effects are negligible and the velocity remains essentially constant in the radial direction. This part. This is irrotational core or flow region. You can see here velocity is constant and the friction is negligible. Then hydrodynamics entrance region, the region from the pipe inlet to the point at which the velocity profile is fully developed. This part, from the entrance to this part, when this velocity is fully developed. After this, after this hydrodynamic entrance region, the velocity profile doesn't change. From this point, the profile of the velocity will be like this. But up to here, it is changing to reach this. You can see this also shows the velocity. Hydrodynamic entry length is the length of the hydrodynamic entrance region. This part. This is LH, or this part is LH, or hydrodynamic entry length. Hydrodynamically fully developed region is the region beyond the entrance region in which the velocity profile is fully developed and remain unchanged. This part. This is hydrodynamically fully developed region, when the profile of the velocity is not changed after this point. Why these different regions are important? Because its characteristic, especially this interest, will be effective on the required energy and to design a pump, to select a pump actually, and also it is effective on the following velocity. And from this point, the velocity will be constant, and we can just use the average to have the velocity. And this L is not always small. Sometimes we can have just imaginary L to have this fully developed velocity profile. Okay, so this is for entrance region of the flow inside the pipe. That was for the velocity profile. What about temperature? We have a similar figure you can see here for the temperature. Again, this is flow. When flow comes to the pipe, it has a average or uniform temperature as Ti. When it goes through the pipe, its temperature will change. Why? Because it has a heat transfer with the pipe wall. So due to the heat transfer between the fluid and the pipe wall, its temperature profile will be constantly changing to finally reach something like this, which its temperature profile is fully developed. After this point, the temperature profile doesn't change. It will be something like this. Temperature near the surface is or in contact with the surface is same as the surface, and at the center is different. Depends on the temperature difference between the fluid and the pipe wall. So again, we have different region for this. Thermal entrance region, which is the region of flow over which the thermal boundary layer develops and reach the tube center. All of this is the thermal entrance region. All of these figure you can see here. Thermal entry length, the length of the thermal entrance region. This one, thermal entrance region up to here, when the temperature profile is changing and it does not fully develop. Thermally developing flow is the flow in thermal entrance region. It is thermally developing flow, which is the temperature of the flow is changing to reach a constant profile. Thermally fully developed region is the region beyond the thermal entrance region, in which the dimensionless temperature profile remains unchanged. This one. This part is thermally fully developed region. And fully developed flow is the region which the flow is both hydrodynamically and thermally developed. This one is important, and which we are interested about that. Fully developed flow, you can see here we have a fully developed velocity. This is fully developed temperature. We call a fully developed flow when it is fully developed thermally, it's fully developed, and also it is fully developed velocity. So we call that fully developed flow when its temperature and velocity profile is not changing anymore. Why it is important? Because now we can use this definition to calculate the heat transfer actually. Hydrodynamically fully developed, so it says that the velocity or relative velocity is not changing. In other words, rho u r and x by rho x is equal to 0. This equation simply said that the profile of the velocity is not changing. Rho u r and x is by rho x is 0. What it means? It means, you know, here for example, this is rho u and x, or rho u r and x actually. Rho u r and x. This is in x, and here is r. So rho u r and x by x. In this x is not changing. So the meaning of this is that the profile of the velocity is not changing. So this division will be 0. And the velocity or the relative velocity is a function of the r. As you can see here, the change in the difference in the velocity is only dependent on the r, for r from the center. So the velocity is only dependent on the r. What about thermally fully developed? Thermally fully developed also says that the temperature profile is not changing. In other words, Tsx minus Tr and x. Temperature of the surface, Tsx for example, minus Tr and x. For example, this is r at this point again as x. This is Tr and x divided by Tsx minus Tmx. Mx is T mean temperature. So Tsx minus Tmx is our reference. Tsx minus Tmx, which is the medium temperature. So this difference divided by this reference is not changing. In other words, it is fully developed. The temperature, if we it means that if we again draw something like this, will be exactly same like this. From now on, all of this will be same. The profile will be like this. The meaning of this part is this. The profile will be same from this point onward. So we have these two equations. Now we are interested to calculate the surface heat flux, for example. A surface heat flux is Q dot S equal to Hx Ts minus Tm. This is convection between the fluid and the surface. You know this equation? This equation is Newton's law. You can remember that. Hx Ts minus Tm. Ts is the temperature of the surface. Tm is the average temperature of the fluid. Is equal to K rho T divided by rho R. This is the conduction. The heat transfer from the center or from any part of the fluid to the region near the surface is by conduction. So we can write this K rho T divided by rho R for R equal to R, when R is equal to R at this part. So we have conduction, for example, from center to the near the wall in the fluid. It is equal to heat transfer from the fluid to the wall of the tube. So we can write this equation. Then Hx can be calculated by this equation, which we are interested to know that. That fully developed region give us a possibility to have an assumption. As you can see here, imagine this is a flow. At the fully developed region, this is entrance region, this is fully developed region. This H or Hx, which we have calculated here, is not changing anymore. It is constant for the fluid and the surface. This heat convection coefficient H is constant. Hx at this part will be H. It's a constant value. This is why this is the reason why this fully developed region is important. Usually we are interested to calculate this LH, which was the entrance region, or LT, which was the velocity region, entrance region. So we are interested to have these two L. Then by knowing this L, we can find the H, and we can imagine the H is constant. Also for friction, we have same trend. The friction for fully developed region is constant. These two are important, and we can use these two assumptions for our calculation. So how we can calculate this entry length? By this equation. For laminar flow, the hydrodynamic entry length is equal to this value. LH for laminar is almost equal to 0.05 Reynolds number times D. D is here from now on. D is the hydraulic diameter. It can be for circular cross section, duct, or any other cross section. And thermal entry length, or LT, for the laminar flow is equal to this much. PR is Prandtl number. And for turbulent flow, hydrodynamic entry length is this much, 1.359 the hydraulic diameter times Reynolds power 1/4. And thermal entry length for the turbulent flow will be almost 10D, which is equal to hydrodynamic entry flow as well for thermal entry length. This LH and LT are the characteristics which I mentioned we are interested to know. Why this is important? Because after this length we can consider the flow as to have a constant H and constant friction, constant convection coefficient and constant friction, and our calculation will be much easier.